The narrative of the Great Flood is one of the most enduring and debated accounts in human history. For millennia, the story of Noah's Ark has been interpreted primarily through a theological framework, viewed by many as a test of faith and by others as a mythological allegory. However, in recent years, a different perspective has emerged from the intersection of archaeology and naval engineering. When the vessel described in the book of Genesis is analyzed, not as a religious symbol, but as a tangible structural object, the details reveal a level of technical sophistication that challenges our assumptions about the ancient world. If we strip away the artistic interpretations often found in children's literature and focus strictly on the raw data provided in the ancient text, we are confronted with a massive engineering project. Genesis 6:15 provides specific dimensions: 300 cubits in length, 50 cubits in width, and 30 cubits in height. Converting these ancient measurements to the modern metric system, we find a vessel approximately 450 feet long, 75 feet wide, and 45 feet high. To put this into a modern context, the Ark was roughly equivalent to the length of a standard American football field and stood as tall as a 4-story residential building. While critics often point out that modern steel cruise ships can reach lengths nearly double this size, such comparisons overlook the vessel's primary function. The Ark was not designed for propulsion, speed, or steering. It had no need for a sharp bow to cut through the water, or a powerful engine to drive it forward. Its sole engineering objective was buoyancy and stability in the face of extreme maritime conditions. The genius of the Ark's design lies in its geometric proportions. The length-to-width ratio of 6:1 is widely recognized in naval architecture today as an optimal balance for stability in turbulent waters. In modern maritime engineering, this specific ratio is critical because it minimizes the risk of capsizing by keeping the center of gravity low while distributing buoyancy evenly. Recent studies conducted by naval architects using wave tank simulations confirmed that a hull with these specific dimensions would possess a high degree of hydrodynamic stability. Unlike a sailing ship designed to slice through waves, the Ark's box-like structure was intended to ride atop the swells. This design would allow the vessel to withstand the monumental torsional forces generated by chaotic, multi-directional waves that would snap a longer, thinner hull in half. The structural integrity was further reinforced by the materials and construction techniques described in the text. While the identity of gopher wood remains a subject of scholarly debate, with theories ranging from cypress to a hardened cedar or even a processed laminate beam, the coating method is explicit. The text mentions the use of pitch, or bitumen, applied both inside and out. This substance, known for its sealing properties in the ancient Near East, provided the necessary watertight integrity for a year-long submersion. From an engineering standpoint, a thick coating of bitumen would serve a dual purpose: waterproofing the vessel and increasing the structural flexibility of the timber, allowing the hull to expand and contract under the immense stress of the ocean without fracturing. However, building a ship that can float is only half the equation. The far greater challenge was keeping the cargo alive. A fundamental question that skeptics and engineers alike have asked is how a crew of just 8 people could manage the biology of thousands of animals in a closed system for over 370 days. The logistical hurdles, specifically regarding waste management, food distribution, and ventilation, were immense. With a daily output of animal waste estimated in tons, manual disposal would have been physically impossible for such a small crew. Structural analysis suggests that the Ark likely operated as a passive machine, utilizing natural forces to reduce human labor. To handle the massive volume of waste, The vessel likely utilized gravity-fed systems. Historical models propose that the animal enclosures were constructed with sloped or slatted floors. As the ship rocked with the constant rhythmic motion of the ocean, waste would be naturally directed away from the animals into specific channels or troughs running behind the cages. These channels would logically converge on a central reservoir or a moon pool system on the lowest deck. Here, the pressure differential between the water outside and the air inside could be utilized to flush waste directly into the ocean through controlled sluice gates. This semi-automatic system would explain how sanitation standards were maintained without the need for modern electrical pumps or hundreds of sanitation workers. Food preservation and distribution required a similarly automated approach. The inventory had to include enough grain, hay, dried fruit, and seeds to last for more than a year, a diet carefully planned to meet nutritional needs without rapid spoilage. It is plausible that a system of large hoppers or silos was located on the upper decks to take advantage of gravity. Grain and water could flow down through a network of bamboo or hollowed wood piping to troughs on the lower decks. A single crew member could simply open a valve or pull a lever to feed hundreds of animals in a fraction of the time required for manual feeding. This efficiency was not a luxury, it was a necessity. Perhaps the most sophisticated, yet often overlooked aspect of the design was the ventilation system. In a sealed wooden box filled with thousands of breathing, waste-producing creatures, the accumulation of carbon dioxide, methane, and body heat would become lethal within days. The biblical text describes a specific feature known in Hebrew as the zohah, an opening finishing 1 cubit from the top of the vessel. This was not merely a window for light, but a critical component of an ancient HVAC system. Engineering principles suggest this design utilized the stack effect. As body heat from the animals warmed the air in the lower decks, that air would naturally rise. The central upper opening allowed this stale, warm air to escape continuously. This rising column of air would create a pressure vacuum, naturally pulling fresh, cooler air into the vessel through lower structural vents or the permeable nature of the upper construction. This passive air exchange cycle would ensure continuous atmospheric renewal without the need for mechanical fans. Beyond the engineering of the ship itself, the biological inventory presents another layer of complexity. A common objection to the Ark narrative involves the sheer volume of biodiversity. How could millions of modern species, from beetles to bears, fit within a vessel of these dimensions? The answer lies in understanding the biological distinction between the modern scientific classification of species and the biblical classification of kind or men. Contemporary research in the field of baraminology suggests that Noah did not need to collect every specific variation we see today. For instance, he did not need a German shepherd, a wolf, and a coyote. He only needed a single pair of the ancestral canine kind that possessed the genetic diversity required to repopulate those lineages over time. When this taxonomic consolidation is applied, the total number of animals required on board drops significantly. Estimates suggest approximately 6,800 individuals. Furthermore, biological logic indicates that many large animals were likely transported as juveniles or sub-adults. Younger animals are significantly smaller, consume far less food, produce less waste, and are generally more resilient to the stress of confinement. This strategy would have reduced the required cargo space to less than half of the Ark's total capacity, leaving ample room for the extensive food supplies and the living quarters of the human crew. We must also consider the psychological reality of this voyage. For 370 days, 8 people lived in a state of constant confinement.
the acoustic environment alone would have been overwhelming. Studies suggest that the sound of a global storm beating against the timber hull, combined with the vocalizations of thousands of animals, could exceed 85 decibels, comparable to the noise level inside a busy factory. Maintaining mental health under these conditions required strict discipline. The crew likely lived by a rigid schedule of maintenance, inspection, and feeding, governed by the cycle of oil lamps rather than the sun. This routine was their anchor in a chaotic world. The conclusion of the voyage marked not just the end of the flood, but a fundamental shift in human existence. The world the survivors stepped into was drastically different from the lush, greenhouse-like environment of the pre-flood era. The landscape was likely barren, rocky, and hostile. To adapt to these new conditions, the biblical text records a major theological and biological shift. Genesis 9:3 marks the first authorization of meat consumption for humanity. This dietary transition from a purely vegetarian existence to an omnivorous one reflects a pragmatic adaptation to a post-cataclysmic ecosystem where plant life was scarce and survival was difficult. The construction and operation of Noah's Ark, when analyzed through the lens of logistics, naval architecture, and biology, reveal a project of immense complexity. It describes a vessel that was not only plausible, but remarkably advanced. A structure designed to preserve life through the mastery of physics and resource management. Whether one views this account as a literal historical event or a profound cultural narrative, the engineering principles embedded in the text offer a fascinating glimpse into the capacity of ancient knowledge. It remains a testament to the concept of survival against impossible odds, leaving us to wonder how much ancient wisdom has been lost to the tides of time.